Hi everybody, in this video we're going to talk about proof writing and we're going to go over the difference between two-column proofs and coordinate geometry proofs. So here on the left I have a proof for us to take a look at first, and notice how this proof does not have any numbers. It has given information and it has a proof statement that we're going to have to arrive at through logic and reasoning. So this is going to be a two-column proof with a statement reason chart because there are no numbers. Later on in the video, we will see examples of coordinate geometry proofs where there will be numbers, and we'll use formulas and calculations in order to prove our conclusion. So taking a look at the given information, it says that BD bisects angle ABC. And I see angle ABC is right over here. And if that angle is being bisected, that means it's being split into two congruent parts or equal parts. And those equal parts would be angle 1 and angle 2. So that's my first conclusion that I can draw from my very first given. I'm going to go ahead and I'm going to mark that in the diagram. Since I do have a chart already started over here, I'm going to fill in the corresponding given information and the conclusion that we just drew. So we just started with the information that BD bisects angle ABC that was given. We always start a proof with our given information because that is the basis for all of our further conclusions. They're all based off of what we have in the givens and our logic and reasoning. We just concluded that since this angle was getting bisected, angle 1 is congruent to angle 2. And that's because we have an angle bisector that splits an angle into two congruent parts. Moving on to our second piece of given information, BC is congruent to CD. I'm going to go ahead and mark that in my diagram so I can see it clearly. And I'm going to put that here as my second given. BC is congruent to CD. Now let's think about what conclusion we can draw from that. Now that we know that BC is congruent to CD, I know that it is an isosceles triangle with two equal sides. And triangles with two equal sides also have two equal angles. And specifically, those equal angles are located across opposite from the congruent sides. So here are our two congruent sides of triangle BCD. Opposite from this congruent side is angle 3, and opposite from this congruent side is angle 1. So now we see that angle 1 is congruent to angle 3 because we have a triangle with two equal sides. So the angles opposite those two equal sides must also be congruent. So I'm going to put that conclusion from our second givens in our proof. Angle 1 is congruent to angle 3. And once again, that's because since two sides of triangle BCD were congruent, the angles opposite those sides also had to be congruent. If a triangle has two equal sides, it's also going to have two equal angles. And you'll learn that later on in the next unit as well. Now, let's think about what conclusion we can draw. Angle 2 is congruent to angle 1, but angle 3 is also congruent to angle 1. So if angle 2 is congruent to angle 1, and angle 3 is congruent to angle 1, since they're both congruent to the same angle, that means they have to be congruent to each other. They have to have the same measurement as each other. And that's the transitive property. When two angles are congruent to the same third angle, or segment, so I should say things instead of angles. When two things are congruent to the same third thing, that means they're congruent to each other. So for example, in this past example, since angle 3 and angle 2 were both congruent to the same angle 1, that means they had to be congruent to each other. So I'm going to mark that in my diagram. Angle 2 is congruent to angle 3. And that's going to help me reach my goal. My goal is to prove that line CD is parallel to line BA. Now, when we're trying to prove things are parallel, we're going to think about our angle relationships. Because when parallel lines are cut by a transversal, we have a bunch of angle relationships that are true. We have congruent alternate interior angles. We have congruent alternate exterior angles. We have congruent corresponding angles, supplementary same side interior angles. So the reverse is also true. If we can find any of those angle relationships here, that would prove the lines had to be parallel in the first place to make those angle relationships that are true. So here, I'm proving that CD is parallel to BA. And I like to highlight my lines I'm proving parallel and the transversal that intersects them. And here I see my letter Z. And letter Z's are really nice because when you have a letter Z, in the corners of the Z are your alternate interior angles. Inside the lines, on different sides of the transversal, alternate interior angles. And guess what? We already proved that these alternate interior angles, angle 2 and angle 3, were congruent to each other. And since we have congruent alternate interior angles, that's one of our ways of proving that the lines are in fact parallel to each other. Since alternate interior angles are congruent, the lines are parallel. Moving on to our next example, and we're going to write a 2-column statement reason chart because once again, there are no numbers. We have something given, we have something we need to conclude, and we have to use logic and reasoning to get there. So first off, we're told that GE bisects angle DGF. I'm going to put that down as step 1 in my proof. GE bisects angle DGF, and that is given. Here's angle DGF, and if it's getting bisected, that means it's being split into 2 equal parts. And here, those 2 equal parts are angle 2 and angle 3. I'm going to get that down in my proof as well, because I just drew that conclusion. Angle 2 is congruent to angle 3, and we're going to use our same reason as the previous example when we also have an angle bisector. An angle bisector splits an angle in 2 congruent parts. My goal is to figure out something about angle 1 and angle 2. But I already know the relationship between angle 3 and angle 2. So if I can say something about angle 1 and angle 3, then I'll be able to relate them all to each other, which is what I need. I'm taking a look at angle 1 and angle 3, and I know this, a letter X. And there's a letter X because they're formed by intersecting lines. And when we have intersecting lines, they form congruent vertical angles. We really like letter X's because when we have letter X's, we have those vertical angles which are always congruent. I'm going to put that down in my proof. Angle 1 is congruent to angle 3. Intersecting lines form congruent vertical angles. And now that I know the relationship between angle 2 and angle 3, and angle 1 and angle 3, I'm now all ready to make the statement that I need to make about angle 1 and angle 2. Since angle 1 is congruent to angle 3, and angle 2 is also congruent to angle 3, they must be congruent to each other, since they're both congruent to the same angle 3. If it's easier to see it in the proof, we have angle 1 and angle 2, both congruent to the same angle 3. So that means they have to be congruent to each other. And that's transitive property. If 2 things are congruent to the same third thing, then they have no choice but to be congruent to each other. And that's it. Moving on. In the next example, we have AB is congruent to CD. Let me start making my 2-column chart so I can transfer as we go along and we don't forget anything. And that is given information. we need to reach the conclusion that AC is congruent to DB. For a second, if you take a look at AC, you'll notice that it's longer than AB. And if you take a look at DB, let me use a different color for that. If you take a look at DB, you'll notice it's longer than CD. So we're starting with shorter segments than what we actually need, and we want to end up with longer segments. When we're going from smaller to bigger, that tells me we're going to be using the addition postulate. So now we just have to figure out what we are going to be adding together. So let me leave some space for myself and we'll write out the addition. So we're starting with AB over here, and we want to end up with AC. So we need to think about what can we add on to AB, what can we stick on to the end of it, so that we go from AB to AC. And you might see that the missing piece is BC. BC is what we need to add on to AB to make the full segment AC. So I'm going to put that here. AB plus BC makes AC. We're also starting with information about CD. And we're trying to make DB, to get information about DB. So we have to think about what are we going to add on to DC, what are we going to stick on to the end of it, so that we go from just having DC to having DB. And you might say, well, if I start with DC and I add on CB, then I get the full segment DB that I'm looking for. And that is addition postulate. I'm going to write that down here. And CD plus CB makes DB. Now let's make sure our addition is valid. When you're using addition or subtraction postulate, you have to be starting with congruent and then adding or subtracting congruent. So we know our starting segments AB and CD are congruent because that was given information. But now we have to ask ourselves, are the two things that we're adding on, BC and CB, congruent to each other? You might be thinking yes, because they have the same two letters. If you take a look at the diagram, BC and CB are the same exact segment as each other. And we can also tell that because they have the same two letters. So they're naming the same line segment. And we do know that any line segment, anything, has to be congruent to itself. That's reflexive property. So we do know that BC is congruent to CB. We just actually do need to state that in our proof before we can use addition so that our addition will be valid. So I'm going to put that over here. BC is congruent to CB. And that is the reflexive property or postulate. And now I can fill in my numbers. And all that's left is for me to justify my last step of my proof with a reason. Let's think about how we're going from step 3 to step 4. We're saying this plus this is this. We're replacing the addition with what it actually is, with what it's equivalent to. Same thing here. We're saying this plus this is this. We're replacing the addition with something that's equivalent, with something that means the same thing. Think about our math word for replacing. If you're thinking substituting, you're absolutely right. That's substitution. We're just replacing the addition with what it actually is. Substitution. And there we go. Last one for 2-column proofs before we move in to the coordinate geometry proofs. So we're starting off with knowing that angle ABD and angle CDB are right angles. I'm going to put that into my diagram. Angle ABD and angle CDB are right angles. Let me get that in my proof. Angle ABD and angle CDB are right angles, and that is given information. We're also told that measure of angle 2 is equal to the measure of angle 4. and I'm going to put that here, that is given information. We need to show that angle 1 is congruent to angle 3. Now, it might seem pretty obvious to you that they are congruent because angle 1 and angle 2 together make 90. Angle 3 and angle 4 together make 90. And since angle 2 and angle 4 are the same, angle 1 and angle 3 need to be whatever number will make the 90 with whatever there. For example, if angle 2 is 30 and angle 4 is 30, then that means angle 1 and 3 both have to be 60 degrees to make that 90 degrees. They'll have to be the same thing as each other to make 90 degrees with whatever other is the value there. But we actually have to write this up in a 2-column statement reason format. So let's keep on going. What I'm going to say next is that angle 1 and angle 2 are complementary. And I'm also going to say angle 3 and angle 4 are complementary. And I know this because angles that form a right angle or 90 degrees are complementary. That's the definition of angles that are complementary, that they together make a right angle. And now I'm all ready to prove my proof statement. And this is a little shortcut. It's a theorem called, oops, let me erase that. Complements of congruent angles are congruent. All that means is since angle 1 and angle 2 are complementary and angle 3 and angle 4 are complementary to each other, and since angle 2 and angle 4 were congruent, since angle 1 and angle 3 were both complementary to these congruent angles, they have no choice but to be congruent to each other. Complements of congruent angles have to be congruent. And that's it for this proof. Now we have a coordinate geometry proof, and already you can see the differences. Already you can see that we have a grid, which is always optional on the Regents exam, but I highly recommend that you do plot your points so you can see the shape clearly. You have coordinates, numbers, and you have something that you need to prove that can be proven with a formula. We're not going to write a 2-column statement reason chart for a coordinate geometry proof. We're going to choose our formula that we're using, show all of our work, and then end with a sentence explaining what we proved and how we know it. And we call that sentence a concluding statement. And yes, you do need that to get full credit on a coordinate geometry proof. I'm going to just take a second and graph the triangle so we could see it better. And I see that we're proving in part A, well, we're determining if triangle ABC is equilateral, isosceles, or scalene. Equilateral means 3 equal sides. Isosceles means only 2 equal sides. And scalene means no equal sides. So in order to see which one it is, I'm going to have to find the side lanes and compare. And we know that when we're finding lengths of sides or line segments, that is the distance formula. It's the distance between 2 points, between A and B, between B and C, and between A and C. So I'm going to take a second and I'm going to plug into the distance formula. I'm going to pause my video while I do that so this video isn't 3 hours long. Please do the same and then you can compare your answers. Please pause the video while you do your own calculations. And here I have my distance formulas, and you can see that none of the sides are the same length. And you can see that I ended with a concluding statement. Triangle ABC is scalene because all the sides are different lengths. Now in part B, we need to determine if triangle ABC is a right triangle. We have 2 different ways that we can do this. The first way is we can use the Pythagorean theorem because that will only work if we do in fact have a right triangle. Remember, if you're plugging your side lengths into Pythagorean theorem, your longest side does need to be plugged in for the hypotenuse, which is C. So that would be radical 125 would have to be plugged in for C. I'm going to do it using slope formula because if we do have opposite reciprocal slopes, That means lines are perpendicular, which means they form a right angle. So if side AB and BC did have opposite reciprocal slopes, that would mean that they were perpendicular, which would mean that they would form a right angle, making this a right triangle. I'm going to pause the video while I use the slope formula. Notice that when I did my slopes, they worked out to be opposite reciprocals. So that does mean that they are perpendicular, meaning they form a right angle, making the triangle a right triangle. Okay, for this next one, it's another coordinate geometry proof. And we need to show that XM is the perpendicular bisector of YZ. Perpendicular bisector is two parts, perpendicular and bisector. The perpendicular part can be shown with slopes because we do know that perpendicular lines have opposite reciprocal slopes. So first I'm going to find the slope of XM and the slope of YZ and show that they are opposite reciprocals of each other. As you can see, since XM and YZ have opposite reciprocal slopes, they are perpendicular. The next part is showing that XM is a bisector of YZ. Two ways you can do that. Either you can use distance formula and you can show that YM is congruent to MZ, or you can do what I'm going to do in this video, and I'm going to show that M is the midpoint of YZ using midpoint formula, because a bisector, since it cuts in the middle, should pass through the midpoint of a line segment. So I'm going to find the midpoint of line segment YZ, and I'm going to show that it is point M, which would make XM the bisector. And notice when I did the midpoint formula of YZ, I did in fact get the coordinates of point M, which are the points 4, 4. So I ended with the concluding statement: since XM is perpendicular to and bisects YZ, it is the perpendicular bisector of YZ. Last question over here. We have a triangle. Owen claims the median from point E must pass through point G. Is Owen correct? Explain why. Remember, a median is a segment in a triangle that connects a midpoint of a side to the opposite vertex. If we're told that the median here is from point E, that's a vertex. So it should be drawn from the vertex to the midpoint of the opposite side. So what we're verifying is whether or not G is the midpoint of side DF. And that will tell us if we have a median or not, if the median needs to pass through point G or not. So right now, I'm just going to find the midpoint of side DF. As you can see here, when I found the midpoint of DF, it was the point 5 over 2, 1/2. It was not G, which has the coordinates of 3, 1. So since G is not the midpoint of DF, Owen is not correct, and the median from E, typo, the median from E would not pass through point G. It would pass through the point 5 over 2, 1/2.